We are going to describe another finite difference representation model for the diffusion equation we have here, and that's called the Crank-Nicholson method. So basically, it combines the stability of an implicit method with the, you remember that this method was unconditionally stable, with the accuracy of a method that's second order, that's going to be second order both in space and time. So here simply remember that the implicit method we had before was second order in space, but first order in time. So simply here, we are going to take basically this method, we can see that method as an average of both the explicit and implicit forward time centered space schemes. So we're making this average both at left and right hand side at the time step at j plus 1/2. So that's actually the strategy that we're going to follow. So let's consider this is the timeline that's centered around some specific point on the space that's characterized by index n, and this is the timeline. So that will be a point located at n and time j, and that will be another point which is located at the same space n at time j plus 1. So in this case, delta t, which is the time step, will be the time difference between these 2 points. And we're going to take an intermediate point here with the same index on space, n, and the index on time will be just in the middle. So we're going to call it j plus 1/2, so that the time step from here to the next point will be delta t, the half of delta t over 2. So basically the strategy is that we are going to consider the expansion of this, both the partial derivative of u with respect to time here and the second order partial derivative of u with respect to x here on the diffusion equation around that intermediate time we have here. So basically, first we are going to start with the finite difference representation of the partial derivative of u with respect to time. And for that, we are going to take the Taylor expansion we do have here, actually both Taylor expansions around this point here, in order to have an approximation of the u function both at this point and this other point. So these are the 2 Taylor expansions up to second order on delta t. So here you can see that the approximation of the u function evaluated at this point is going to be the u function evaluated at that intermediate point plus the partial derivative of u with respect to time evaluated at this intermediate point here, where times the time step from here to here, which is delta t over 2, plus 1/2 the second order partial derivative of u with respect to time evaluated at this intermediate time here, plus the time step from here to here, delta t over 2, the square of that, plus the next order is going to be delta t to the 3rd power. And the same with that, the only difference between the 2 is that this is actually forward in time with respect to this intermediate time, and the other one, the previous one, is backward in time, so here delta t is going to be negative, so the only difference is that the linear term here is negative, but the other rest, it's actually the same. And as our goal here is to have a finite difference of the partial derivative of u with respect to time, actually we'll have to take one minus the other, so that because that's negative, this is positive, so in order to keep this linear term, have to make one minus the other. And doing that, you have this minus this one, these 2, they cancel each other, 2 times this one, and these 2 also cancel, so the accuracy of this expression here is going to be the power of delta t. So the next, the goal here again is to have an expression for this one. So basically from here we clear this one, and clearing that one we have finite difference of this expression here. So this is what we have, which actually is the same as the one we have for both explicit and implicit approximations, and the accuracy of that is, as we know, is the square of delta t. Okay, so the next step is to have an approximation, a finite difference representation for the second order partial derivative of u with respect to x here. And we are going to have a finite difference representation for that, which is evaluated around this intermediate point. I want it to be accuracy of delta, the square of the delta t as well. So basically, we are going to follow here the same strategy. We're going to make a Taylor expansion of this function here, because this is a function actually which depends also on x and time. And we are going to have a Taylor expansion of this function around these intermediate points in order to have an approximation for the partial derivative of u with respect to x, or the second order partial derivative of u with respect to x at these 2 points. So that's what we are going to do next, and this is here. So these are the 2 Taylor expansions. Actually, they are just linear Taylor expansions. We are making Taylor expansion of this second order partial derivative of u with respect to x evaluated at around this intermediate point in order to have the approximations for this function at these 2 points. We're just keeping, we are making here, you can see here that the space here is the same. Basically, we're doing the expansion here on time, so this will be the linear term. So here we have the partial derivative with respect to time of this function. This is the function we are considering in the Taylor expansion, times the time step going from this intermediate point to the next one, which is delta t over 2, and the next term is going to be which is actually the error in this Taylor expansion, the square of delta t. So here the next, or the approximation for the previous point here is going to be actually pretty much the same. The only difference is the linear term, that's its negative again. So the goal here is to have an approximation for this one. So we have to remove that one, and an approximation for this one, which is accuracy, which accuracy is going to be the square of delta t. So for that, we are basically going to take the sum of these 2 expansions so that this intermediate, those linear term will vanish. So summing these 2, we have here the sum of these contributions. It's equal to 2 times this one, plus the order, or the error is going to be the square of delta t. This is what we wanted actually. So just from here we clear that, and we have the partial derivative of u with respect to x, or the second order partial derivative of u with respect to x evaluated at this intermediate point is just the average of this, the partial derivative of u with respect to the second order partial derivative of u with respect to x evaluated both here and here. So this is just considering the time evolution, and besides that, what we need is a finite difference representation, therefore, for this one, with this one. So here we have, which is for the partial derivative of u, or second order partial derivative of u with respect to x evaluated at time j plus 1, and the same but evaluated at time j, which wants, and we want to be it accurate on the square of delta x. But we already did that, because that will be the one we had for the explicit approximation, which is this one here, and this one corresponds to the final representation we had for the implicit method, which is the one we have here. So actually, as you can see, therefore, and calculating the second order partial derivative with respect to x, we're making an average of the final difference representation we have for the implicit method and the one we had for the explicit method. So yes, taking collecting all the information we had both for the partial derivative of u with respect to time and for this one, and putting the same line, that's the result we have. This is the final difference representation for this Crank-Nicholson method we have for the diffusion equation, which is the accuracy of this approximation is second order accuracy both on time and space. That's what we have. So as a next step, I'm putting it more in order. Basically, what we are going to do, as it's quite usual, we're going to put to the left everything which depends on j plus 1, and we're going to put on the right everything which depends on j, and that's basically what we're doing here, from going from his to this one. So, and this is actually what we have. This is the finite difference representation we have for the Crank-Nicholson method. This is the one that we have to apply here. So this actually, the n we have here goes from 1 to nx minus 1. So this is the number of equations we do have. Alpha here has the same value as we had defined before. Here, of course, there are more unknowns. Here we have nx plus 1 unknowns. So these, the missing two equations are supplemented as it happens in the other methods by the boundary conditions. You have two boundary conditions, one here and another one. And again, we have here the same problem we had for the implicit method. There is no way of clearing from here an expression for the u functions at different points evaluated at j plus 1, just as a function of all different u functions evaluated at time j. So there is no way of clearing that in a direct way. So here, as it happens in the implicit method, in the full implicit method, what we will need is to deal with the matrix representation in order to work with that and use the matrices in order to clear the u vector evaluated at time j plus 1 as a function of different u points evaluated at time j, because actually these equations are can be applied at any j. So the idea again is to have, as in any method, is to have the u function at some point at some specific time and use them in order to have then the u functions at the next time step, and so on and so forth, in order to fulfill and have this all the u values of all the mesh on time and space. But in order to do that, it will be much more efficient to use the matrix representations for the method.